Hello, my name is James Gleason, and today I'll be presenting RLScope, which is a tool that we have built for profiling deep reinforcement learning workloads. RLScope is an open source tool that you can find on our GitHub page, and I encourage you to download it so that you can profile your own RL workloads today. Deep reinforcement learning has made a lot of progress over the past decade, from applications as diverse as learning robotic locomotion from scratch using just a reward function, to even data center management. Unfortunately, this progress is severely limited by training time. It takes up to 40 days to train AlphaGo 0 from scratch using 4 TPUs on a single machine. To make matters worse, the profiling tools we use today to understand training time are not well suited to RL workloads, since they focus on GPU time in bottleneck layers and less on CPU time. You may be asking yourself, why not just focus on supervised learning and let RL indirectly benefit? In this work, we observed that RL workloads have 3 key differences compared to supervised learning that fundamentally changes their workload profile. First, the training data. Supervised learning uses large pre-labeled datasets that can keep the GPU busy by overlapping sending mini-batches to the GPU with computing backpropagation from the previous mini-batch. In RL, training data must be collected at runtime by interacting with a simulator that often runs on the CPU. Second, the training loop. In supervised learning, Python is only used when initializing the computational graph and does not typically execute within the core training loop, whereas in RL, Python must be used to glue together the core training loop operations, like inference, backprop, and simulation. Third, neural network size. Supervised learning uses large neural networks. ResNet can have up to 156 layers, whereas RL uses smaller neural networks, like AlphaGo 0, which has only 39 layers. Together, these 3 characteristics make it difficult to know where an RL workload spends its time, whether it's on the CPU or the GPU. To address this challenge, we built the RLScope profiler. RLScope makes the observation that although there are many different RL algorithms, fundamentally they all have common high-level operations in their core training loop, and we can use these operations to scope CPU and GPU time across the RL software stack. RLScope's API allows developers to add these operation annotations to their training loop code. In order to collect cross-stack information across different deep learning backends and simulators, RLScope transparently intercepts transitions between Python and native libraries and transparently registers hooks and CUDA libraries to record low-level GPU activities. To prevent CPU time inflation, RLScope calibrates and corrects for profiling overhead to ensure accurate insights. RLScope derives its insights by linearly scanning the cross-stack event trace. By performing this cross-stack analysis, RLScope can simultaneously scope training time to different resources like CPU and GPU and their overlap, and different high-level operations. Using RLScope, we surveyed RL workloads across different algorithm types like on-policy and off-policy algorithms, different deep learning backends like PyTorch and TensorFlow, and different simulators, from low-complexity simulators like computer games to high-complexity simulators like robotics and drone tasks. From our survey, we found that on-policy algorithms are up to 3.5 times more simulation bound than off-policy algorithms. We found that certain deep learning backends can introduce more transitions from Python to backend C++ libraries, and this increase in transitions can lead to more CPU time inflation. In particular, we found a 2.3 times slowdown in a TensorFlow implementation of an RL algorithm compared to a PyTorch implementation. Furthermore, for simulators, we found that at least 38% of training time is in simulation, even in the simplest of simulators. For scale-up RL workloads that try to increase GPU utilization by parallelizing inference requests, we found that coarse-grained tools can report 100% GPU utilization, even though RLScope reveals that the true GPU-bound time is actually quite low. In fact, across all these different RL workload dimensions, we found that GPU usage was low, at less than 14%. This illustrates that GPU utilization is a characteristic unique to RL workloads and will be a fundamental challenge in optimizing them further. RLScope is an open source tool that you can find on our GitHub page, and I encourage you to download it to profile your own RL workloads today and make your own insights. With that, I would like to thank you for your time, and I look forward to meeting you at our poster session.